Hello and thank you for watching. In this video we're going to prove a couple more theorems relating to convergence of sequences. So firstly we're going to say that convergent sequences are bounded. Okay, to prove this, let's first say that for all epsilon greater than 0 there exists an n such that for all n greater than this n, we have xn minus x being less than epsilon. So that's the definition of convergence for a sequence xn. Now, from this definition, we can choose our epsilon as long as it's greater than 0. So we can say that xn minus x less than 1, for example, and this choice of epsilon doesn't really matter, but I chose 1 just to make it simple and easy. So now, by triangle inequality, we have that xn minus x, the modulus of these, is less than 1. Okay, now, from here, we have that xn is less than 1 plus modulus of x. Okay, so now we have that this xn, this sequence, is bounded by 1 plus the modulus of x for n being greater than our big N. So for n being greater than n, we have xn being less than 1 plus x. Amazing. Okay. So now, the reason why we wanted to do this is because we wanted to get rid of our infinite case. We wanted to get rid of our tail. So now we can focus on the finite terms preceding it. Okay. So now, suppose that we have m equal to the maximum from the modulus of x1, x2, and so on, all the way to xn, big N, and then this thing here after it. So we're saying m is the maximum value from all of these preceding terms, and then for n being greater than n, we know that xn is smaller than this, the modulus of xn is smaller than this. So we have that xn, modulus of xn, is less than or equal to m, because if we have xn, if we have n greater than our big M, n, we have it being less than this. Otherwise, we have it being less than or equal to this. And so it's always bounded, the modulus of xn. But hang on, this is the definition of bounded. Hence, xn is bounded by m. Okay. Well, I guess we can say plus or minus m, it doesn't really matter. But, great. Okay. So our second theorem is theorem, we have monotone, monotone and convergent, sorry, and bounded sequence is convergent. And actually we call this the monotone convergence theorem. Okay, so there's two cases for this. It's either going to be increasing or decreasing. I'll only prove it for one case and then leave the other case as an exercise, but it follows in basically the same way. Okay, suppose an is an increasing sequence such that an is always less than or equal to n. Okay, now at the very start of the real analysis playlist, we said that as long as we have a bound, so some bound, then the supremum must exist by the completeness axiom. So let S equal sub an. So now we have S minus some epsilon is not an upper bound. For epsilon greater than 0. And this is the case because our S is the smallest upper bound we have, so anything smaller than it cannot be an upper bound. But then this means that there exists an n for which an is greater than S minus epsilon, since it's not an upper bound. Now you may already see where this is going. If you do, you may want to pause the video, complete the proof yourself. But I will carry on now. So for n being greater than this big N, we have that an is greater or equal to an, since we have an increasing sequence. So every term after our big an is going to be even greater than it. And so that means that S minus epsilon is less than an, which is, since S is a supremum, S plus epsilon. That is the modulus of an minus S is less than epsilon for n greater than n. But then hang on, this is just the definition of convergence. That means therefore not only does an converge, it also converges to the supremum. Nice. And that is the proof completed for one half. Now I'll leave the viewer with some exercises. So exercises. The first one, I'll write it as an I instead because it's more appealing. Prove bounded decreasing sequence an converges to the infimum. Okay. Now, second one is a little bit of a challenge, which I'll cover in the next video on the real analysis series. However, for now the viewer can attempt it themselves. It's something. I'll proceed another proof. Prove every proof that every sequence has a monotone subsequence. And the reason why this is a challenge is not because it's an extremely hard problem, it's rather because the idea is non-standard and may be tricky to come up with, but after you get the idea, it's a really easy problem. Okay, thanks for watching, hope this video helped in some way, and yes, bye bye.